Today we're going to be talking about the greatest integer function. Now the greatest integer function has other names. It's also called the step function. You may hear it referred to as the step function. And I've also seen it called the floor function. So you know there are some other names for it, but the idea with the greatest integer function is that it takes the input, the x value, your domain, and finds the greatest, or finds the integer. Now, what is an integer? If you have forgotten what an integer is, it's those numbers on the number line, positive and negative, but it doesn't include fractions or decimals. So it's just like the number line numbers, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, an integer, closest to that number without going over. All right, without going over. Now, what does the greatest integer function look like? Because all of our functions have had some distinguishing characteristic. What is it that looks like it? Quadratic has to have a squared in it, cubic has to have a cube in it, and square root has to have a radical in it. You know, everything has its symbol. So the symbol for the greatest integer function is a bracket. Sometimes you will see it as a single bracket, and sometimes you'll see it as like a double bracket like this. All right, so that is the greatest integer function. It's not just straight bars. That would be absolute value. And so this is the greatest integer function. It wants to find the integer closest to that number without going over. And I always kind of think about Price is Right, the game show. Remember, whenever you're bidding on stuff, you want to get the closest price to it without going over it. And so I always kind of liken it to that. So if we're thinking about the greatest integer function here, if I want to take the greatest integer of 7.35. So again, integers don't have decimals and don't have fractions. So the greatest integer to 7.35 without going over it would be 7. And so that would be 7. Now I couldn't do 8. 8 is close to it, but 8 would be bigger than it. 6 wouldn't work because there's another number closer to it than 6 is. So 7 is the closest integer without going over. If you think about it on the number line, you know, decimals always happen in between the little numbers on the number line. So here is 7, here is 8, here's 7.35. When we're talking about greatest integer, we're always trying to find that bar that's immediately to the left of it, because the one on the right of it's bigger than it. So we're always looking to the number on the left. Now, negative 2.5, that's where we have to be careful. If we think about negative 2.5 on the number line, here's negative 2, here's negative 3, here's negative 4, here's negative 1. Negative 2.5 is right here. Here's negative 2.5. So we want the integer that is the closest to it without going over it. So when I look, that's over here actually at negative 3. A lot of students try to say that the greatest integer function just gets rid of all the decimals. Well, that's not true. It's trying to find the integer closest to it without being bigger than it. This cannot be negative 2. Negative 2 is bigger than negative 2.5. So the greatest integer without being bigger than negative 2.5 is actually negative 3. Fractions, don't let fractions trip you up. Fractions just need to be turned into decimal form so that you can understand them, you know, easier or make more sense of them. If I've got 4/3, that's roughly 1.3333 blah 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 blah. So the closest number without being bigger is 1. Negative 10/5, well, negative 10/5 is actually exactly negative 2. So when you do get a number itself and it has no decimal and it has no fractions, well, the greatest integer of that number is that number. Negative 2 is not bigger than negative 2. So it is allowed to be equal to negative 2. So that will just be negative 2. So this is what the greatest integer function is. So let's take a look at some tables just so we can kind of get an idea of what the graph would look like. So looking at this table, the greatest integer of negative 2 would be negative 2. Negative 1.75 would be negative 2, negative 1.5. These are all rounding down to negative 2. But then when I get up here to negative 1, well, that's going to be equal to negative 1. Well, then this would round down to negative 1 and to negative 1 and to negative 1. But then when I get to 0, oh, well, 0 can be 0. 0.25 will round to 0. 0.5 will round to 0. 0.75 will round to 0. Then when I get to 1, jumps up to 1. 1.25 will be 1, 1.5 will be 1. So this would be all of these values. Well, if you notice, they kind of come in clumps. These all have the same value. I go negative 2, and then all the in-betweens, negative 1.75, negative 1.5, negative 1.25. You know, all of those, it basically makes this straight little line here. But then at negative 1, it hops up to negative 1. And then again, these all fill in here all the way until we get to 0. And then at 0, it hops up here. So I'm getting this step shape. All of these are constant functions. They're getting the same number, but then they hop up and go up. Notice at negative 2, it's equal to negative 2, but then when it gets all the way to negative 1, it hops up here. What this does mean is that we have to take advantage of closed and open circles, because this is going to be all these decimals all the way up to negative 1, but it's not going to include negative 1. At negative 1, it's going to jump up. And then this is going to include all of these decimals until I get to 0, and then at 0, it's going to hop up. And then this will include all the decimals until it gets to 1. And then it's going to hop up. If we don't use the open and closed circles, then we don't pass that vertical line test. We don't want to forget our vertical line test. You know, it can only go through one point. So if both of these were closed points, it wouldn't pass that vertical line test. So we've got to make sure that we've got the open one down here where it finally jumps up to the one above it. So watch out for your open and closed circles. We want it to pass that vertical line test. But now you can see why they sometimes call this the step function. It looks like a series of steps. It is an example of a piecewise function, and next week we're going to be talking about piecewise functions a little bit. Piecewise functions are functions that are made up of a bunch of different little functions, and this one is made up of a bunch of little horizontal lines. That's what it looks like. So if we think about this as the parent function, we have transformations. We can shift it left and right. We can shift it up and down. We can reflect it, flip it over the x-axis, or flip it over the y-axis. And we can stretch it. We can stretch it vertically, and we can stretch it horizontally. We'll talk about that in just a minute. So we need to know what are the important parts of this graph so that we can know how to transform it. So things to remember is it's just like all of our other graphs. It has a place to start, all right? And when it's not transformed, it starts at 0, 0, when it's in its basic form. What it needs is it needs a width. Each one of these steps is got a certain width to it. The default width is 1. Each step is 1 wide. It also has a height. Notice that there is a gap between each step. What is that height, the gap in between each step? Well, the default is 1. So it starts at 0, 0, has a width of 1 and a height of 1, and its default is positive going up from left to right. So it's got this positive slope. And so those are the things that we can flip. The other thing to remember is that the step has the closed dot on the left and the open circle on the right. That's going to be important because if we flip it left to right, if we transform it by reflecting it left to right, then we have to flip that as well. All right, so let's take a look at some example graphs. Now, here's some things that we don't want to forget. Our graphing form. So we've got y equals, and then we could multiply by a number up front. And then we've got our double brackets. We could multiply by a number inside. We learned that with when we have the negative ones and stuff with square roots and cube roots. And then we've got our x minus h, because that's how we shift it left and right. Close our double brackets, and then we could add something outside. So these are all of our transformations that we are familiar with. So now our starting point, if it's going to be transformed, and it's not going to be at 0, 0, we know this moves us left to right, this moves up and down, so our starting point is always going to be at hk. So our default is 0, 0, but now we know that we can transform it, and we can start at hk. Now, we know that our default is for our steps to be 1 wide and 1 tall, but that can be transformed. Anything multiplied on the outside transforms it vertically. So if I multiply it by a on the outside, instead of it going up 1, it's going to go up whatever a is. So this tells me how tall my steps are. Multiplying on the inside of a function, everything inside a function always changes it left to right. So by multiplying the inside of the function by a number, I'm going to change the width of my steps, the length of my steps. And so what I need to realize is everything inside is backwards. So I'm not going to multiply 1 by b, but I'm actually going to take the default 1 and divide it by b to figure out how wide my step is on the inside. So this gives me my width of my step, and this gives me the height of my step, and I know where to start my step, and that really gives me everything that I need. Now, I do need to remember that if a is positive, then the steps are going to go up on the right, up to the right. That's that positive slope. And then if a is negative, then it's going to go down to the right. So whether your steps are going up or down depends on whether it's positive or negative. So we want to keep that in mind as well. So let's take a look at this example. All right, here's our first example. So let's get some important pieces of information here. I've got my h and my k. So I always do the opposite of the inside number, keep the outside number. That's the same for all of our functions. So I'm going to start at 3, 1. I've got a number multiplied by the outside, so it's going to have a height of 2, and then its length, the width of the step. There's nothing on the inside, so my steps are just going to be 1. So now I can actually graph my graph. So I need to go to 3, 1, 3, 1, and that is my starting point. I know that my step has to be 1 wide, so I'm going to put the open circle over here, and I'm going to draw a step. That's 1 wide. And then I know that my step needs to be 2 tall. So when I go here to my open circle, I'm going to go up 2, and that is where the next step is going to start. So it's 1 wide, so open circle on the other end. There's my step, that's 1 wide. Over the circle, I go up 2 to get to the next step. So as long as we know where to start, we know how wide our stair is supposed to be, and we know how tall our stair is supposed to be, then we can just continue on that pattern. So I can go back in the other direction because technically this does keep going in the other direction. So here I'm going to go down 2, and this end has the open circle, and then I know that it's supposed to be 1 wide. Then I can go down, so we're just continuing it on backwards in the other direction. We can follow the pattern. They're all still 1 wide. They're all still 2 apart from each other. I always have an open dot above a closed dot above an open circle. I don't want to have any closed dots on top of closed dots because then it wouldn't pass a vertical line test. So we know where we started, we knew how wide our stairs were, and we knew how tall our stairs were. In the second example here, we want to remember what we talked about with square roots and cube roots and absolute value. If we've got this number inside, we do have to factor it before we find our vertex. So we've got to get it in graphing form. So I'm going to factor out the 2. If I factor out the 2, then I have x plus 2. So this is really y equals bracket 2 times x plus 2, and then my bracket minus 5. So when I look for my starting point, opposite of the inside, -2, keep the outside, -5. Now, if I had not factored this out, I would have gotten it wrong because I would have put in 4. But we have to factor out that 2. Our height, there's no number up front, so it didn't get stretched, so they're still just 1 apart. But we do have a number inside, which is changing how wide our graph should be. So I need to take 1 and divide it by that number, which means that all of my steps need to be half wide. So they're really teeny tiny little steps. So I'm going to -2, -5. Here's where I'm going to start. All right. Now, I may actually want to make my life a little bit easier and make it so that it's a half. These things are going to be crowded. So I'm going to make myself say 1, 2, 3, 4. I'm going to make each block a half to make my life a little bit easier. I am the master of my graph, so I can decide what I want to count by and give myself a little more room. Even Desmos does that. You may have noticed that it'll change what it's counting by to fit its needs all the time. So I want to go to -2, -5 if I can get it to fit. So -2, -1, 2, 3, 4. Oh, we'll make it work. Here is -2, -5. I know that it's only a half wide, so I go half for my open circle. And then I know that I'm going up 1. So I'm going to go up 1, go half, go up 1, go over a half, and go up 1, and go over a half. And we just continue the pattern. Up 1, over a half, up 1, over a half, and then we can continue on up in this direction. So the 3 pieces of information you've got to get is your starting point, how wide are your steps, and how tall are your steps. I did want to show you on Desmos. When you go on Desmos, you can do these in Desmos, but it has a name for the function. It is called, they do call it the floor function in Desmos. So if I put in floor, then I could type in, it was 2x plus 4, and you just use parentheses, and then I believe it was -5. And so then you can see, they did like we did. They counted, every 2 was 1, so they could get the halves on there. I will tell you this, Desmos does not, it does not do the open closed circles. It doesn't do the dots. But if you notice, if you're tracing along the graph, when you pick a point, it's right here exactly, and then it's decimal, 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 decimal. But as soon as I get over here next to 0, like I'm almost to 0, as soon as I get to 0, it jumps up. So it does not have it equal at that point. It just doesn't do the open circle.